In this screencast, we will be looking at two experiments by which are included in the CBSE syllabus. They are not included, unfortunately, in the HSC board syllabus, and it does happen sometimes that in the JEE main examination, which is conducted by the CBSE, I have seen questions based on these experiments appear, and this screencast is therefore to familiarize you with these two experiments, which are actually very simple. If you just know the experiment, you'll be able to solve those questions quite easily. So the first experiment is to find the resistance of a galvanometer using the half deflection method. Now I'm sure that you remember that in the HSC syllabus you have something called Kelvin's method. It's there in the syllabus, at least as far as 2015 is concerned. So the Kelvin's method is a method which helps you to find the internal resistance of a galvanometer. However, the half deflection method of the CBSE syllabus, it's quite different from Kelvin's method, and it helps you to do the same thing. So let's have a look at the circuit first. As you can see, in the circuit there is a source of EMF. So I've shown two batteries in series, and the circuit diagram doesn't show any internal resistance associated with the battery, and that's exactly what the assumption which is made in the practical is that the battery is ideal. So on the internet I have typically seen demonstrations in which these two batteries are basically, it's a single 1.5 volt dry cell. I've seen in one demonstration at least. So although it has some internal resistance, I suppose that the internal resistance is quite small and it doesn't play a major role in the calculations. So in other words, although you use practical batteries in the experiment, you are going to assume that they are actually ideal. Now this resistance, it's actually a variable resistance, so I can put an arrow over here. Okay, I'll just remove it, but it's actually it's a resistance box, and you are supposed to plug out a sufficiently high resistance from that. So it's typically called a high resistance box, HRB. Okay, and on the other hand, okay, let me go to the other part of the circuit, this one. That's obviously it's the galvanometer whose internal resistance is to be found. And in fact the second experiment to find the figure of merit is also included. It's the same circuit. You can do both experiments using the same circuit. So we have to find later on the figure of merit of the same galvanometer. And if you just go through this part of the circuit, you see that it's a very simple circuit, but there is in between in the circuit there is a key K1, and that basically if you plug in the key over here, then the current flows, otherwise there is no current, obviously. Now this branch over here, it's connected in parallel with the galvanometer, and it consists of a shunt resistance, which is typically a low resistance. In fact this too has to be a variable resistance, although I won't write that symbol. It's a resistance box, and it's typically called a low resistance box because S is small as compared to R. So low resistance box, I can say LRB. So that's the shunt. And of course the key over here, K2, you may plan to plug in the key or you keep it open, so that will determine whether current flows or not in that part of the circuit. Of course, that's assuming that key K1 is closed. Now, how do I conduct the experiment? So in the first part of the experiment, what is done is key K1 is closed, which means that it behaves like a short circuit, and K2 is kept open. In other words, the operative part of the circuit is the lower loop, and the upper loop is open circuited, right? So there's going to be current flowing according to that arrow. And what you do is to plug out some suitable value from the high resistance box, okay, and you just then measure what is the deflection in the galvanometer. Okay, so that's the first part of the experiment. With K1 closed and K2 open, find the deflection in the galvanometer. Now you have to remember that this galvanometer, it's a very rudimentary galvanometer. So what I mean is, you will have a scale. You will of course have 0 marked over here, and there will be divisions on either side, but there might not be any numbers written. It might not be, it's usually not calibrated, okay, in amperes or in milliamperes. So that's the needle, and what you're going to do is, you just, when I said you measure the current, you basically have to measure what is this deflection. Now this deflection, I'll call it theta. There are two ways to measure it. It can be measured in degrees. That would be if these marks which I've shown on the dial, they correspond to degrees, or if they don't correspond to angle, or they don't correspond to degrees, you can just measure theta in divisions, number of divisions. So in the first part of the experiment, you find what is the deflection of the needle in terms of degrees or in terms of divisions. And one recommendation which they usually or at least sometimes they do give is, you have to manipulate the value of capital R by removing suitable resistances. Remember, it's a resistance box, so it's a variable resistance. You have to manipulate it so that theta is even. So the number of divisions or the number of degrees is even. And the reason for this is that in the second part of the experiment, we have to manipulate things in such a way that the current through the galvanometer is half of the original current. So theta should become theta by 2, and of course, if theta by 2 is actually marked on the scale, and that's possible if theta is even, so theta by 2 will then be an integer, then it's possible to take a more accurate reading. That's why we try to manipulate things in the beginning so that theta is even. Now let's assume that the total EMF in the battery or in the batteries is E, and let's also assume that the voltage across the galvanometer is V. Now the this particular branch can be ignored because it's open circuited, and so I can apply the potential divider formula to calculate V. V is of course equal to G divided by where G is the galvanometer resistance, G divided by G plus R, this whole thing multiplied by the total voltage across the series combination of galvanometer and R. That total voltage is nothing but the battery EMF, assuming that the battery's internal resistance is negligible. So this I must multiply by E, and that is my first equation. Now in the second experiment, of course, what is done is the key K2 is closed, so that means that there is going to be current flowing in this particular branch. This K2 is effectively now a short circuit. So now the entire circuit consists of two loops, the lower one and the upper one, and you have current flowing in both the loops. You now manipulate the shunt resistance S. Remember, it's a resistance box. You manipulate it in such a way that the galvanometer reading, which was originally theta, now becomes theta by 2. What this means is that the current through the galvanometer is halved, and it also means that the voltage across the galvanometer, which was formerly V, is now V by 2. You can now apply the potential divider formula again across the series combination of R and the G parallel S combination. So this entire thing, okay. So by the potential divider formula, the potential difference across this part of the circuit is equal to, the total voltage is still E, because we have assumed an ideal battery, but this time in the numerator is going to be the parallel combination of S and G, and divided by the total resistance is that S parallel G in series, so plus R. So that's my equation number 2, and of course I'm supposed to substitute in place of S parallel G in both these places S multiplied by G divided by S plus G. And after doing that substitution, equation number 2 becomes this equation. Now if you recall, the aim of this experiment was to find the value of G, and you have got two equations involving G. So I think very obviously what we have to do is to divide one equation by the other, so these V terms get cancelled, the E terms also get cancelled, and you get an equation involving G and S and R. Remember, S is known because it's the resistance of a resistance box, and likewise R is also known for the same reason. So I suggest that you just do the manipulation yourself in your notebook, and finally you will arrive at a very compact equation, that is the galvanometer resistance is the product of S and R divided by the difference of R and S, and since R is larger than S, it's very easy to remember that you must write R first followed by minus S. That's the formula for the galvanometer resistance when you're trying to find it using the half deflection method. So if you look at the formula, you realize that it's almost, not exactly, but almost as if the galvanometer resistance is the parallel combination of S and R, but for this minus sign. So if you want to remember it as a mnemonic, you could say it's the anti-parallel combination of S and R. So just if you go back to the circuit again, you just see that the circuit in the first step it doesn't contain this branch because K2 is opened, it only contains the lower branch, and in the second step the upper branch is also included, and the value of G, which is to be found in this experiment, it is the anti-parallel combination of R and S. So if it was S, if S were to be in parallel with R, then it would have been SR upon R plus S, but as a mnemonic I'm using the term anti-parallel. Please don't use it actually in other places, but since it's an anti-parallel combination, it's not R plus S in the denominator, it's R minus S, and since the series resistance R comes from the high resistance box, it's going to be larger than the low resistance box resistance S. So R comes first and S comes later. You have to memorize this formula, very easy, using the anti-parallel mnemonic, and you can very easily solve questions. You have to know the circuit and you have to know the formula. So that's what is needed as far as the JEE main is concerned if they ask you a question based on the half deflection method. Now if you recall, this experiment has two parts. So now we have done this part, we'll try to look at the second part, which is to find the figure of merit of the galvanometer. Now the figure of merit is basically the current through the galvanometer divided by the deflection. So the figure of merit is galvanometer current. So remember, I'm talking about the current through this branch. Okay, that's the galvanometer current. I'll call it IG, and I want to divide that by the deflection which that current produces. So you know, in SI units it would be amperes per radian, or you could say amperes per degree if you want, or if you're not measuring theta in degrees and you're measuring it in divisions, the figure of merit could be measured in amperes per division. Now to find the figure of merit, it's only the first part of the experiment which is relevant. The second part is not relevant, and therefore I will just remove this, okay, because that part of the circuit is redundant. It doesn't have any function in the second part of the experiment. Okay, so in the first part of the experiment you are passing a current IG which flows through R as well as through the galvanometer, and you're supposed to figure out what is this, the figure of merit, which is IG divided by theta. Now theta, of course, you measure in divisions or in degrees by direct observation, and IG you can find by applying KVL to the entire circuit. So it's going to be E divided by the total series resistance is R plus G. Okay, so R of course is known from the resistance box, and G is something which you have calculated in the first part of the experiment in the half deflection method. So although this particular shunt resistance and all that is not involved in this formula, however, the experiment which you did with the shunt resistance actually gave you the value of G, and that's the value you're going to substitute over here. And that's why the experiment in which we find the galvanometer resistance using the half deflection method, that is to be done before the experiment on the figure of merit. So in short, the figure of merit is directly given by E, that's supposed to be known in the experiment, divided by R plus G. G is found in the half deflection method, and in the denominator you also have theta, which is measured by direct observation, and that gives you the so-called figure of merit. That's how these two experiments are done in the CBSE syllabus.